Good evening. Now we'll start our week 4 lecture. So, so for that I will share the screen now. Hope you guys can hear me. Okay. Okay. So this is our week 4 class. So continuation with the previous lecture, I'll be starting with spectrophotometer to analyze the wastewater samples or any other wastewater in the sense it's if even if it's from industry or any other kind of wastewater, we can do the elemental analysis, also the amount of filaments present in the wastewater through the spectrophotometer. So this is the when you see the screen here, you can see the screen. This instrument is the main part of the system, and here it is connected to the laptop, no, the system which can calibrate, and you can see the visual information, and with the plotting we'll get through the screen. So here, this is the chamber. This thing, particular cap, we can open like this. See here, here we can just open this way, and this is the chamber, and we have a tube like this is a tube like structure. This is a tube, a glass tube. Okay, I think people are joining now. It's very difficult for me to. Okay, so here you can see this chamber. We can this glass tube is there. In this tube we are filling the wastewater. This is the tube. Here you can see the tube. So in this tube we are filling wastewater, and then keeping inside and securing with the cap. This we have secured with the cap. So then, for each element present in the wastewater, the absorbance will be different. So what we are doing is, we inside this, there is, here you can see, here the light will transfer to the wastewater tube, then differing the wavelength and absorbance data we will derive. So for each element, the absorbance will be different. So accordingly, the system will calibrate and give you the presence of element and how much the particular element is present in the screen. Like that only a spectrophotometer works. And this is for the liquid sample. There is another equipment also there for the powdered sample, also with the thin pellets, thin sheets also we can do. But here, this particular instrument specifically for the liquid samples. Okay, now, any doubt in this? Okay, now we'll go for the reactors. So why the reactors are using? So to treat the wastewater, we can use different types of reactors. So the reactors can feed with the microbes or with the chemicals to to process the wastewater. Inside it, the ingredients can break down, and then like that we can treat the wastewater. Specifically, that that bioreactors are there. So if you use different types of chemicals, we can use chemicals also, or we can use microbes. We can use chemicals or microbes for that. So Here these three are the different types of reactors. Here you can see the reactor which is in the batch reactor, and this one is continuous stirred tank reactor, and this is plug flow reactor. So the detailed lectures, I think you guys already heard from the YouTube. And now this is like what is in batch reactor. You see that this is the inlet and this is the outlet, and this is the what this is the liquid, that handling liquid, and we apply a stirrer, and this is continuously stirring to make sure the mixture is uniformly mixed. But here what you do, you fill the water, and then what you're doing, you just close the system, and the system is now you are not putting any liquid inside. This is completely closed, and now you are working with the inside liquid. So here when you see the continuous stirred tank reactor, the stirrer is there, but the difference is you are giving feed, and also there is byproducts producing, and it is continuously in inflow and outflow motion. You are providing the feed solution at a specific rate, flow rate. At a specific flow rate, you are continuously giving some solution, handling solution, and then it is processing inside, and the byproducts are removing simultaneously. So this particular system is a continuous flow system. It is continuously in, you are providing the handling solution. So now the plug flow reactor is this one. In plug flow reactor, here you are not providing any stirring, but you are just continuously feeding it and the products you are collecting. In plug flow reactor, normally you will add some baffles like this here. So the input liquid, it will come and it will flow like this manner. Okay, so here you are, by providing this, this stack, this baffles here, you are increasing the path length. So you will get more time. The handling liquid will get some time in inside the chamber. Here you are not increasing the length of the chamber, but you are just providing in between some stopping, some the some some restrictions like this, so that its flow will be like like this, so that it will take some time to reach from its inlet point to outlet point, thus increasing the path length. Also it get more time to process. So these are the three main different reactors. And here you can see that chemicals you can add, also microbes also you can add. But when you add chemicals, different chemicals into the water, and it will react with the pollutant or different elements which is present in the uh, handling liquid. And what it is doing is, okay, so what it does is it is producing a lot amount of byproducts. So when it comes to this handling the byproducts which is formed by these chemicals are a huge challenge. So because these chemicals, again we have to, the byproducts which is produced by adding these chemicals, again we have to process it. It is a big challenge. So at this time, adding microbes is quite sustainable way of treating the wastewater in this reactor chamber. Okay, so now first question. uh, yes, yes, this one, right? Yes, yes. So here in, yes, yes, in batch reactor we are close, like we are stopping the inflow. Yes, 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 yes. Plug flow also, the plug flow in, we can add in the continuous mode also. Mainly we have seen a lot of continuous mode of operation. So we can continuously feed the liquid, and the byproduct we can simultaneously collect it. But the here is we are not the mixing is in through this way, it is not fully mixing. And also here the baffles we are providing to increase the path length, so it gets more time to process. Here the other type of reactor, it is like if it's a vertical or this horizontal, it is like this much time it will take. So but if it's the path length is like it, each time it is getting more time at each point without increasing the spatial, the size of the length or thick, size of the whole reactor. We are just increasing the effectiveness of the treatment is increased. Okay. Okay. So now, first question: transformation or degradation of pollutants in natural water body may be due to four options are given: biotic, abiotic, C photo degradation, D all of the above. What is the answer for this? Transformation or degradation of pollutants in natural water bodies. So if there is a natural water body, so water is there and there is okay, just okay. You said C. uh, think more like it's a natural water body, and there will be microbes can be there, and it's getting light from sun. Also it is there's a atmosphere is there which is at normal condition. So it what type of reactions it can, the degradation can happen. So the answer is all of the above. Okay, so it can be biotic, it's an together, okay. So it's a natural water body. So where the water body is in connection with the atmosphere, and the atmosphere has a lot of oxygen, and also the water body has microbes, and with the microbes, the microbes will take part in the degradation, and the biotic and abiotic condition also can exist in different layers of the water body. And photo degradation means at daytime there is a lot amount of sunlight also it is getting. So for a natural water body, we are not closed enclosure, it is a natural water body. So there all these things can take part in the degradation of the pollutants. Okay. Yes. Yes. Yes, photo degradation take place in daytime. Yes. Yes. Okay. Now, second question: aquatic animals are more vulnerable to lowered DO. DO means dissolved oxygen in options: evening in winter, early morning in hot summer, C high stream flows, all of the above. Which one is the answer? Any guess? Yes, right. B is the right answer. Why? What is the reason? Yes, that is right. And yes, that is right answer. And also here in hot summer means at night also, night we know that there will be, one thing like what is the in the earth on earth, when we tell about the maximum oxygen production, from where it is coming, who are the main source of oxygen? Plants, but it's not, you're saying the, yeah, but plants are there, but more than the what we are seeing, the when we look at around, we see the trees or small plants, we think that it is the mostly the oxygen is from them, but oxygen is mainly from water bodies where the phytoplankton is there. So they are the main source of oxygen. More than 70 percentage of oxygen that we are seeing is mainly due to this. Okay, so that is like here. At night we know that these we are not getting sunlight here, so the oxygen is production is less. So morning, early morning time, when the intensity of light, so sunlight is less in the morning. So here when we take the binaural variation of the sunlight, we see that this is from 6 a.m. to this is 2 p.m. and this is again 6 p.m. So you know that at early morning the intensity, so intensity of solar radiation with respect to time. So when we see that from morning it will start racing, and you see that at around okay, we see that at around 12 to 2 p.m., that it depends on the area. Mainly the peak temperature is around 12 p.m. to 2 p.m. So most of the cases it is around this time it will peak, and then it will start decrease. So morning the intensity is less, so the photosynthesis also it won't happen that much effectively. So at early morning, okay. Okay, at early morning, when we see the oxygen in the water will be less, because even they are just started the mechanism of producing oxygen. And also, we know at the summer, this water will be hot, the top layer will be hot, and it can hold lesser oxygen compared to the cold time. And also at this summertime, what happens? The layer stratification happen. What is layer stratification? So here always we know that when the temperature of a water layer is high, and then more hot water will be arranged in the top layer, and the cold layer will always be in the down. That is due to the density, more density for cold water. So that means the even this process, because of this process, you know the mixing of water layers will also be less. So if the fishes are in this layer, water layer mixing water layer mixing is less at during the hot summer. Because of this stratification, the layers will be arranged like that. So even the if the top layer have little bit oxygen also, the mixing of the layer doesn't happen, so the oxygen is not properly dissolved in the cold layer just below this hot layer. So for all these reasons, when we campaignly say that in the hot summer, the oxygen availability in the top layer will be less because of this water stratification. Even the mixing with the cold layer, these layers also not happening. So the oxygen which is reaching in the cold layer also will be less. So the organisms, mainly this aquatic animals which are staying in the top layer, also in the down layers, will not get enough dissolved oxygen for their for their daily, for their uh, needs. So that is the main reason. It is not due to the high stream force. So these all three and options are wrong. The answer is early morning in the hot summer. The answer is clear. Okay, thank you. Then third question: very less life forms exist in which zone? Septic zone, recovery zone, decomposition zone, and reaeration zone. Which one? Uh, where less life forms are there? That's the question. Less life is there in, you're saying in decomposition zone, but decomposition zone means what is happening? Which one? D. No. Re-aeration means there is more of there is re-aeration. Aeration is there. So you yes, that is the right answer. Septic zone is the right answer. Why? Septic zone has a region where the dissolved oxygen is very low. Dissolved oxygen is very low. So this is that's why the septic zone is prone to the life forms. Like here, the organisms which need oxygen for their daily, their body doesn't allow to grow in the septic zone. Okay. Okay, next question. Optimization and design of treatment unit is based on, so this is about reactor, what wastewater treatment reactors. So this reactor, I hope you guys have seen the lectures, right? Hopefully you guys have seen the lectures and have analyzed this balance equations and all, you already have learned, right? Okay. So this reactors, when we take, this is wastewater reactor, which I explained even before 3 slides. So in these all reactors, what is the optimization, or how we design a system on the basis of how can we design a reactor? What is the basis of the design? Is this energy balance, sodium balance, mass balance, or momentum balance? What do you think? Any guess? Yes, right. Absolutely right. Yes, mass balance is the main, because mass balance, we know mass balance. We know that what is mass balance. We called it for continuity equation, right? Continuity equation. So why this is, because we need amount of flow which is going in is equal to, there is continuity equation, there is no form of energy, the energy can, this amount of mass which is going inside will come outside, or if there is some reduction in the mass, it actually considered to the generation or reduction of the species inside the reactor, right? So this is the reactor. So if we give some flow, this is mass flow, inflow. So this is the amount of mass, and here we collect some of mass out. So if you say mi is equal to, if you say, if there is some generation or reduction of some mass, that we can say that mg. So mi is equal to m naught plus or minus mg. So here, for the wastewater reactors, we are considering continuity equation to design how much flow we need, how much, velocity we can flow the handling liquid. This all are, we are deciding through this equation. Okay. So now the question starts. So this is a simple question. So this type of question, have you guys solved any time? I think you have learned this, right? This questions, deoxygenation coefficient. What is deoxygenation coefficient? Anyone know? Okay, size of it's small. Okay, just 1 minute. I will increase the size. Okay, sorry, you would have told just okay. Now, now the screen. Now you can see. Okay, so we'll solve the question. So you know how to solve this, or what equation that we can use to solve this? Huh? Yes, that the only that one only the answer. Yes. right? So you can start solving. The question is like the equation is kd2 is equal to kd1 into theta the whole raised to t2 minus t1. So here, um, theta is the temperature coefficient. I think you also take theta, you are taking 1.0747, right? Yes. So theta is 1.047. Here the deoxygenation coefficient of a stream at 21 degrees Celsius is 0.17. What will be the deoxygenation coefficient at temperature 27? Find the value correct up to 2 decimal points. So we have to calculate this one, KD2. So this is the deoxygenation coefficient at 27 we have to calculate, and we know what is KD1. KD1 is equal to 0.17 per day, right? So we have this one, and theta we are assuming this value for the operation. And then T2, what is T2? T2, which is this one, 27. T1 is 21 degrees Celsius. So now calculate what is KD2. Yeah, but yes, yes, but here now, like we can assume this KD1 value is 0.17, like which is for the 21. It is like I think for 20 degrees Celsius, it is the the standard, right? Then you will derive KD1, then you put this in this equation, right? But even if you calculate like this, also the answer is close to the value. Because KD21 we are taking now, so if you calculate in that way, and let me know the answer. Yeah, calculated. Yes, right. D. So like that way you have what is the answer that you got? So if you calculate this way, you will get around 0.224 you get, or just closer to 23. Why I took this here? Because 21 and 20, which is almost close. So that's why this way we can directly do and calculate. Haha. So it's close, right? Yes, that's the answer. Okay. So now we go to next question. So what is deoxygenation coefficient? Anyone can explain what is deoxygenation coefficient? Yes, degradation capacity, right? It's a how when we have a reactor and we have the wastewater to treat. So wastewater is there, and if it's a micro bioreactor, what we are doing that we give some microorganism, right? So if we are giving putting some microorganism, then what the rate it is consume the oxygen there, dissolved oxygen to consume the dissolved oxygen to decompose the organic matter present in the wastewater, organic matter in the wastewater. So the rate at which the microorganism degrade the organic matter with consuming dissolved oxygen, that rate is known as deoxygenation coefficient. Okay. Okay, now we'll go for the next question. Yes. Yes. This one per day. You will get here the unit is per day. Yes. Yes. Okay. So now the next question. A steady state in a reactor indicates option A, no reaction is occurring. Yes, yes, yes. Sorry. Okay, okay, sorry. Yes, yes, I will zoom it. Yes. Um, a steady state in a reactor indicates the four options are given no reaction. If a steady state reactor, so if chamber is there, so in the chamber, if it's okay. So this is called steady state. If it's called a steady state, what is the meaning? No reaction occurring inside the reactor. B, the concentration are same everywhere in the reactor. C, the concentrations in the influent and effluent are not changing with respect to the time. D option, all the above. So what will be the answer if the chamber is in steady state? What is the statement? What do you think it's right? C, right. C is the right answer. Sorry. Yes. Yes, see. So, because here concentration in the effluent, this is the influent, and effluent means that we are collecting, which is not changing with respect to time. So, the concentration which is in TT, this is also DC out with respect to time. This parameter is not changing with respect to time. That means the rate has become zero. Okay. Now, seven question. A continuous flow reactor usually operates in options are steady state condition in long term, B transient condition after its startup and before attaining equilibrium, C both A and B are right, C none of these. What will be the answer? Okay, I will increase the size. Sorry. Yes. So continuous flow reactor. It's a continuous flow reactor, and how the steady when the steady state uh, you know it will come inside the reactor. So what is the right answer? Sorry. Yeah, both A and B are right. Right. So here in a continuous flow reactor we are providing flow continuously. So here the reactor the we are providing inflow and outflow we are collecting. So initially we provide the handling liquid, and then what happens inside the reactor, there will be a time it will take to make it equilibrium. So because now it is not in the steady, first when we start it won't be at a steady, but it will take it, that is called the transient, time. It will take some time, then only it will become steady. Because here there will we are providing and it start the reaction start, then after a particular time the equilibrium state is attained, then after that the system will be in the steady state condition for a longer time as well. We when we are continuing the operation, it will take some time to get the equilibrium. After that it will be in equilibrium state for the longer time, be with providing the inflow and outflow. Okay, next question. Okay, I will increase the size. Okay, okay, just 1 minute, I will connect with the charger. Okay. Okay, now next question. Which of the following statement are false about plug flow reactor? Okay, I have showed the plug flow reactor that first starting of the lecture. This is the plug flow reactor. You have seen, right? This is the plug flow. And you guys already seen the lectures in the YouTube, right? 5 lectures, right? Okay. So this is the plug flow reactor. You can see the plug flow reactor, which I explained you, with continuous motion and which the baffles are in between to increase the path length. Okay, now we go for the question. Okay, so which of the following statements are false about plug flow reactor? Option A, contents remain completely mixed. B, fluid is mixed in radial direction. There is negligible longitudinal mixing. D, example include pipe flow. So here you have to tell which are the statements are false, which is the statement false about the plug flow. What do you think? So you, yes, 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 right. Absolutely right. So here you can see the, see here, see here this this one plug flow. Here it has some, baffles inside. So when you see the, so when you see other, reactors, this stirrer is applied, and whole, oleum is in, in presence, in influence of the stirrer, and it will make the whole handling liquid in a, uniform. But here when you see that it has different, this, this baffles that, so this handling liquid is not fully mixing with each other, so it is flowing like this. So that's why that happens. I hope that you can easily correlate from the, from this figure. So here the content does not remain completely mixed, so this statement is wrong. So others, fluid is mixed in the radial direction and it is negligible, there is negligible longitudinal mixing, and it's an example of pipe flow. So this is about plug flow reactor. Okay. Okay, next, next question. Mass the, okay, I will increase the size. Okay, now you can see, right? Okay. Okay. So next question. The mass balance equation for a completely mixed reactor with first order decay is shown by, there are four equations given. What do you think? You already, if you've seen the lectures, I think it's you can answer this. What is the mass balance equation? What is the mass balance equation for the completely mixed reactor? What do you think? Okay. Answer is A. First equation. Okay. First is the equation. This equation. First equation is the answer for the completely mixed reactor. So you can see the videos, and then you can even you can find the lectures on the derivation also, and you can find out easily how this equation has come. Okay. Okay. Next one. Next one is the problem. You can see this. Okay. This is the question. Okay. See this question here. Uh, a 500 meter cube of CSTR continuous stirring mode of reactor receives water from a single inlet at 40 meter cube per hour flow containing 30 milligram per liter of total polycyclic aromatic carbon. Determine the steady state TPH concentration in a single exist stream if TPH is degraded at first order kinetic with K is equal to 0.25 per hour. So this is the question, and the equation that I showed you in the previous slide, we have to use that equation and we have to solve this problem. Okay, we'll solve. So this type of equation, you guys, anybody have solved? Yes. Yeah, guy, you can. If you have already solved, anyone can respond me. Yes, that is the answer. Yeah, you have solved it now. Okay. Yeah, I will. I will solve it. Just so 1 second. So anybody else got the answer? I just increase the size of the question and I will start. Just- Now the screen is not visible now. In this range, is the screen is visible? No, right? It's very small, right? Okay, I will not able to. Okay, just 1 second. I will. Yes, but my this now like it is in the writing mode. It is. That's the reason. Okay. Yeah. Now it is. Yes. Yes. Now it's visible, right? Yeah. Okay. Now it is. Okay. This problem. Yes. Okay. We'll start solving. So first of all, you write. You have to write the equation, which is the previous equation that in the same slide I have noted. This is the first equation. Write down the equation. Okay. Okay. So here, uh, this first equation we are going to use. So first of all, we will write the non quantities here. What are the things which is given in the question? Yes. So this is first we'll this one, and 500 meter cube of this is the CSTR, and we receive 500 meter cube of water. It will receive 500 meter cube of water. The flow is 40 meter cube per hour. Okay, and this has 30 milligram per liter of total polycyclic aromatic. 30 milligram per liter of TPH. Then we it here it is not at steady state. So what is meant by here steady state means what? Anyone tell what is here? If it's steady state, then how can we say this? Yes, dc by dt equal to what? Yes, right. dt by dc by dt equal to 0. So first we say that this one, what is this 40 meter cube per hour, that is it is entering through a single inlet, that the with the flow rate of 40 meter cube per hour. So that we can write q is equal to 40 meter cube per hour. Okay, then we have also this value 500 meter cube, that is oleum. So this much oleum is coming. So V is equal to 500 meter cube. Then what else they have given? This we have considered 40, 500 considered, and then what is this value? C in, correct. C in. C in equal to 30 milligram per liter, right? Then this one 500, 40, 30. Okay, right. And then apart from this, they have given this information dc by dt equal to 0 from the steady state. Okay, just 1 second. Okay, then now apart from that, one more thing is given, which is k, degradation coefficient, that is here they have given k, they have given this k is equal to 0.25 per hour. Okay, this is the whole known quantities that we got from the equation, and the equation from previous v into dc by dt equal to, okay, okay, what is the equation? Okay, q into c in minus q c minus v k c. So here this term will become 0, right? So the whole term will be 0. Q we know, we already know it's 40. C in also we know it's 30. Then Q we know, Q. C in we know. And then what was the question? We have to calculate the steady state concentration in the a single axis stream. That is this one, C. Yes, C we have to calculate. We have oleum, we have K constant. Then put in this equation and find out what is the answer for C. Yes, 7.27 is the answer. Everyone got it? Got the answer? Okay. So everyone got na? Any doubt is there? Any doubt? Any doubt is there? If anyone is not getting, please let me know. Or any doubt is there? If you want to see the system, also I will tell you. This is the CSTR system. Here, this is the system, central one. Continuous stirrer, tank, reactor. Feed and product we are taking out, and they have asked the concentration at the exist. Okay, got it? Yes. Any different answer you're getting? Let me also see the answers. Yeah. Any doubt? Just the equation that this is the main equation, mass flow, mass conservation equation, which we have learned from here. This is the, this you see the screen here in the equation. Left hand side, dc by dt, it is 0 because of steady state, and remaining all the quantities it is given in the question, directly we are putting this values and we are calculating the c is the thing that which is given in the question. So C is the thing. C determine the steady state TPH concentration of this polycyclic aromatic carbon present in the exit stream. C is the thing that we have to calculate from the this equation. Directly we are putting the values and calculating the C. Right? Any doubt? You're not getting? Just tell me. I think it's Sangamitra, right? Ha ha. You are not getting? Yes. Left hand side, sorry, left hand side is 0. Yes, yes, yes. Q is here 40 into C in this one. And then convert, yes, milligram. Yes, you can just put because the answer is also in milligram. Then, no, no, you don't need to convert because already this thing is in milligram. And here we don't have any other quantity which is in grams. Everything is in meter cube and hour. So you don't need to convert. No, no. This is the C. Okay. See here, Q. which is 0 equal to q means here 40. 40 into c in is 30 minus q is again 40. 40 into c we need to find minus v is 500 into k is 0.25 into c. Yes, 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 c we need to find out. You don't need to convert this milligram because any other no other term is here with grams. Also the answer is in milligram per liter. Okay, got it. Got the answer now. Okay, okay, so we'll do one question which is continuation of this particular question, so keep all these values in mind, this paper. Then we go for the next question. So, with respect to the previous question, what should be the appropriate volume of corresponding plug flow channel? Now it's we are going into the plug flow channel. So previous was what? It is CSTR, continuous stirred tank reactor. Now the same things in plug flow channel. If the same degree of pollutant reduction is needed, if the same that is the and like you should understand the same degree of pollutant reduction is needed, that means unchanged flow rate and K. We have to calculate what should be the appropriate volume of corresponding plug flow. We have to calculate the V. So we should calculate the volume of the corresponding plug flow channel. So in meter cube, we have to calculate in plug flow. So we now here we can see if the people who know the question, na, you can start doing the solving and keep the question. So here we have to consider the previous question values. What is the final concentration of the pollutant that we calculated from this question? That is 7.27 milligram per liter. So concentration in final exist stream, that is 7.27 milligram per liter. And in the initial, it was initial it is given here. See, initially it was 30 milligram per liter. So initial it is 30 milligram per liter, and they have not noted here the same degree of pollutant reduction is needed. So this is the same same degree of pollutant reduction. So here delta C you can calculate here 30 minus 7.27. What is this? You can write down here milligram per liter. So now what is from the first order reaction equation, you can write down here V K C out equal to F naught C naught minus C out. So this equation here, F naught is the flow rate of fluid entering the reactor. This is the flow rate of the that in the previous question which I have showed, this q that we have mentioned here, q flow rate of the wastewater which is entering into the plug flow reactor. So this question is fully for the plug flow, but we are assuming the values of the concentration of pollutant in the previous CSTR question. Okay, here flow rate of wastewater which is mentioned in the previous question, that is q is equal to, in the previous question what was the q value? Q value is 40 meter cube per hour. Okay, so initial concentration this one, final concentration is this here. This is C initial, C out means C final. Okay, so we know this value C initial concentration of pollutant and final concentration of pollutant in the plug flow channel we know. And here this is C out. What is C out here? This is the final concentration of pollutant. What is the final concentration of pollutant here? C out with C final, which is 7.27 milligram per liter. And K, we have the same K value that we have taken in the previous question. That is the rate constant we are taking. What was the K value here? K value is 0.25. 0.25 per 0.25 per hour. So we have to find out the volume of corresponding plug flow channel. Volume, this is the volume. So we have to find what is the volume from here in meter cube. Okay. So I will write this again. You have to calculate the volume of the plug flow channel. So that is equal to initial input flow rate into C initial minus C out, concentration of pollutant inside, concentration of pollutant out, divided by K is the rate constant into C concentration of pollutant in the exit or C out. So from here you will get the volume of the plug flow, that volume of the flow inside the that reactor in the plug flow mode. So calculate this. What is the volume? Calculated? Yes, yes, right. So C is the right answer. So anyone has any doubt? Any doubt? Anyone? So na. So now we'll take 5 minutes break and we will do. So 5 minutes break. Okay. Okay, can we start? So we are going for the next question. So read this question. Okay, we'll start this. Now, this is a simple question. The sewage of a town is to be discharged into a river stream. So the quantity, so there is a river. This is the river. So now what the things are given, the quantity of sewage produced per day is 8.64 million liters. So here the sewage is giving, here it is putting in the river 8.64 million liters. How to convert million liters into liters? Into 10 to the power 6 liters per. Also it is given produced per day. This is actually per day. Okay, so then BOD of this particular sewage is 450 milligram per liter. Okay, if the discharge of the river if the discharge of the river is 300 liter per second and the BOD of the river is 3 milligram per liter, find the approximate BOD of the diluted water. So here for the river also it is given, if the discharge of the river is 300 liter per second and the BOD of the river is 3 milligram per liter. So when this come and mix with the river, find out the approximate BOD of the diluted water. So now we have to go for the balance equation. So what is the balance equation? This is, first we have to take BOD, the total BOD, when these two streams are mixed together. So BOD total I am here giving, and then the flow rate liter per day or hour, here Q, the total, which is equal to BOD of, this is the sewage into flow rate of the sewage plus BOD of the river into flow rate of the river. So this is the equation. Okay, so we put the values into the equation, and the final thing what we have to find is what is the BOD of the diluted water. This quantity we have to calculate. Okay, and also one more thing you have to understand, QT total flow rate is equal to Q sewage plus Q river. Okay, so here first BOD of the sewage, it is given here BOD 450 milligram per liter into QS flow rate 8.64 into 10 to the power 6 liter per day on day. So then what you have to do is you have to convert this into liter per second. How do you convert? So liter to second, how do you convert? If you want liter per second, you have to, here the day is in the denominator. So here you have to, here denominator you have to multiply this day into, day means 24 hours. If you convert 24 hours into 60 means it's minute, then convert to second, again you have to multiply with 60. So now it is liter per second. plus BOD of the river, which is given, sorry, BOD of the river is given here. There is the BOD of the river 3 milligram per liter into QR, flow rate of the river. It's this one, 300 liter per second, divided by this thing, QT, total flow rate. What it's come? This is Q. What is the value of this one? Did you calculate this one? You calculate this value, add this value with the QR. So this is QS plus QR, which is already in liter per second, that is 300. Then you will get the answer. So do it and tell me. First of all, tell what is QT, this value. You calculate it, and QS I have given here for the conversion of liter per day to liter per second. So then do it, and this value is QS. Put it in this here, QS, then add it with QR, calculate the whole value, BOD of the diluted water when the sewage is combined with the river water. Option B. Yes, option B is the right answer. Everyone done? Okay. Any doubt? Everyone done? Yes. Yes, 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 right. So it's easy. Then this is the equation and everything, like we are putting it and finding out. Okay. Now one more question in the same thing. Okay. Uh, no, otherwise next class I'll give that. Okay. Next question will go. Okay. Next question. So the 3 day and 5 day BOD values of a sewage sample are 100 and 150 respectively. The value of BOD, uh, the value of BOD rate constant is, so we have to calculate the K. What is K? So this thing, like we have, so you have to solve a mathematical manner, like you have an equation, you form an equation and you have to find the values from the equation. So that is, equation means one equation you get, then you know that from, if it's x square plus something, okay, x square plus I will give 1, okay, 3x plus 4 equal to 0, then you know how to solve this equation. So it is like minus b plus or minus root of b square minus 4ac by 2a. So ultimately you have to use this particular equation to solve the value. Okay, so now we'll start. So here it is given for 3 day and 5 day BOD values are given. For 3 day BOD values, that is here BOD 3 day, it is 100 milligram per liter, and BOD 5 day it's 150 milligram per liter. So we have to, this is 3 day and this is 5 day, what we have to find is k value. So we know that BOD at time, uh, final BOD, it's equal to BOD initial into, here we, you can see 1 minus e raised to minus kd t, and also here this is the equation, main equation that we have to use. We have final 3 days and 5 days we have. So what you have to do is, so BOD at 3 days is 100 equal to, this is initial value, I'm taking like y0 into 1 minus e raised to minus kd into t, which is 3 here. Okay, then for the 5 days it is final value is 150 equal to initial value that we'll take y naught, and then what you 1 minus e raised to minus kd into 5 days. This is equation 1, this is equation 2. What you have to do is equation 1 by 2, do it, and this 2 will cancel, or 2 by whatever, 2 by 1 or 1 by 2, so you do it, and similar thing cancel, and you will find, you will get an equation. So do it first, till this you can do it. So after that you form an equation with uh, with this minus kd, this value you have to denote in, one term, that x you assume it, the whole term is uh, a cx, then you have to form an equation. Okay, first you reach till here, then we solve. Yes. Okay, can you repeat that once more? Okay. um Okay, I'm not okay. Uh, okay, you. I am just writing here. Just tell me whether that one only. Okay. First, if it's 1 by 2 means 100 by 15, 150. Okay, we'll do like 2 by 1, because then 150 by this 100 will come, right? So then, what is the answer? So here it is 1.5, right? 1.5 equal to 1 minus e raised to minus kd 5 divided by 1 minus e raised to minus kd into 3, right? Yes, yes, yeah, yeah, that way you can do. Then, okay, then it is like 1.5 minus 1.5 e raised to minus kd 3 equal to 1 minus e raised to minus kd 5, this way, right? Then what you have done? Okay, then what? Okay, I will. Other guys have reached. Just 1 minute. Like I will find a place to. So this till here, everyone has reached. So everyone has reached till here. Okay. Um, so everyone has reached till here. Okay. You can see the screen, right? So this is the first one. You are getting 1.5 minus 1.5 into, okay, 1.5 into e raised to minus kd 3 3 equal to 1 minus e to the minus kd into 5, right? Okay. So now how do you deal with this? So now here it become, if you take this one, this is zero point 0.5, right? Then equal to 1.5 e raised to minus kd 3 um, minus e raised to minus kd 5, right? This way, right? Yes. Okay, now we have to solve this equation. So you the final equation is similar to this one, right? For you also, whole number you have taken. Okay. uh Okay, so the, yes, yes, that's, then we will make an equation 1.5 e raised to minus kd 3 minus e raised to minus kd 5 minus zero point 0.5 equal to 0. This is the equation, main equation. So now you have to play with this term and this term. So for example, so make it okay, make it in terms of multiply. This should be like one we can take like square, and then one term we can take like only x. So how do you make it? So here uh, 1.5 e raised to, so kd, okay, minus kd 3. So if we are taking this one, this term as x. See, if we are taking x equal to e raised to minus k d 3, that is 3 kd, then x square means what? X square means it should be e raised to minus 6 kd. So now you have this 5 here. So how do you deal with that? So, hmm. Okay, but if you take that, yes, okay, e to the power minus 5 kd, 5 kd, and then minus, yes, then again it become, yes, minus, um, then it is become 1 kd plus 1 kd, right? This way, e raised to minus 6 kd, this plus 1 kd will come here. Yes. Yeah, but here we have to eliminate the adding term, right? To finalize minus kd. Wait. Okay. So but actually, if it has the, if this is say if it's 2, if this term is 2, for example, 1.5 e raised to minus 2 kd minus e raised to minus 4 kd, then we can actually write this is like, see, if we take 1.5, this is x, and now this one 4 kd is e raised to sorry, here we can take like x square, because here x square means this term only, e raised to minus 2 kd the whole square, which is e raised to minus 4 kd. So like that we have to deal with this equation. Okay. How's- okay, I think it's this one we'll solve in the next. Till here, you have any guys can tell like how we can solve this equation? E raised to minus kd 3 kd minus e raised to minus 5 kd minus zero point 0.5 equal to 0. This is the equation, and we have to find the value of kd from this. Huh? Yes. But that part, like, so if we consider x equal to e raised to minus 3 kd, see, so when we do x square, then it will like, see, e raised to minus 6 kd should come, right? So our assumption, how it become right, that's okay. Actually, I'm solving this question now only. So I thought normally in the previous, in my like questions now, it will come like we can just put like this way, x and x square. I am having doubt in this, so I think, right, what I'm saying is right, huh? So if you put x for this e raised to minus 3 kd, for x square it should be e raised to minus 6 kd, right? Okay. So okay, take this as homework and find out the way. I will also look into it and find out the value of kd, and we'll do this question in the first in the next class. So normally everything now, so this type of question whenever it comes, like, it is always be in this form, so it will be like we can easily calculate like that. It will like 2 days and 4 days, or if it's like 4 days, then it is like 16 days. So I have doubt in this. Okay. So e raised to, sorry, e raised to, e raised to minus 2 kd. Mm, you have solved this, anybody, you solved this this equation, then you can show in the screen, you can share the screen. Okay. So okay, sorry, actually this question I'm solving now only. So so next class, first time, before starting I will complete this. So solve this as a homework. Okay, the final equation we got is this one. The answer is 1.5 e raised to minus 3 kd minus e raised to minus 5 kd minus zero point 0.5 equal to 0. So this is the equation, and you have to calculate kd value from here. What is the kd value? And that is the answer. Okay. So I will take this. Huh. Yes, yes, yes. Yeah. So if this 2 days now, if it's 4 days, we can easily do. And also, yes, 2 square. Yes. Yes. Mhm. Yeah. Yes, yes, that's what. If it's 4, if it's 16, we can easily solve. So anything, if it's come 6 x day, and if this is x square day, we can solve easily. Sorry? Yes, yes, that's what. Yeah, normally this question, it comes like that. So that's why I just came and solved in here only. Okay, so next I will see if any mistake here. I don't know, like this thing, this type I didn't solved. Okay, I thought normally what you said is right. The first day it should be in X form, the next number of days it should be in squared form. What you said, if 2, here it's 4, 4, 16, 3 and 9. Then it is easily we can put what you understood now. Here we can just put in one is like here. If it's 9 here, see here we can put like X 1.5 x minus e raised to, if it's minus 9, then it is x square minus zero point 0.5 equal to 0. And from this equation that which I wrote first, that is minus b square plus or minus root, sorry, here what I have wrote here, this one, where it is. Okay, here see here, this is the equation. We can find out the x value, minus b plus or minus root of b square minus 4ac by 2a. So this manner you can find out the value of x, and this x you can, you got the answer that you will write minus 3kd equal to the x value. For example, you get some numerical 3 or 4, you put this, and natural logarithm, you will inverse this value and find out the value of kd. Okay. Yes. Yes. Sorry. Yes. 10, where it is written, so you're saying this formula you're saying. Okay. Yes, yes, now I can hear you. Yes. 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 Okay, that is logarithm they have taken. It might be logarithm like 10. Huh. Yes. So this way is right. This way is also right. So okay, let me give you another question. Okay, I have some question, solved question in that 2 and 4. Okay, so try solve it now. So then it you will understand. I don't know if there's some mistake is there in the question because 3 and 5. I will try to solve. Okay, now we'll solve the same type of question in 3 and 2 and 4. Okay, so write same question only, but in place of 3 write 2. Write 2 and place of 5 write 4. So the question become the 2 day and 4 day BOD values of the sewage samples are 100 milligram per liter and 150 milligram per liter respectively. So find out the value that K constant from this. Now the number of days is 2 and 4. Got it? What I'm saying? Didn't get? Yes, no? Okay. Now we'll write that. Okay. I will just copy this. So here in this question, I am correcting this 2, 3 as 2 and 5 as 4. Now calculate the BOD rate constant. Now you can do it. So here the same thing, BOD 2 day equal to BOD initial into 1 minus e raised to minus kd into t. and BOD at 4 day equal to BOD initial 1 minus e raised to minus kd into t. Okay, now what you have to do is BOD at 2 days. BOD at 2 days is 100. 100 equal to, here you can take like y naught. Here 1 minus e raised to minus 2 kd, and here 150 equal to y naught 1 minus e raised to minus 4 kd. This is equation 1. This is equation 2. So now solve. Okay, solve 2 by 1 or 1 by 1, and and write the equation like before. Then tell me what is the final equation in terms of e raised to minus that 2 kd or 4 kd, how you reached till that. Okay, you guys have reached there. So 1.5 equal to minus e raised to minus 4 kd divided by 1 minus e raised to minus 2 kd. So it is like 1.5 minus 1.5 e raised to minus 2 kd equal to 1 minus e raised to minus 4 kd. Now if you do, we put this, make this term positive because we are starting with x square here. So this is e raised to minus 4 kd. Then what, okay, minus 1.5. Okay, 1.5 e raised to minus 2 kd. Then 1 minus 1 point, so then my plus zero point 0.5 equal to 0. Till here you reached. Yes. So now you can put this. See this. If you take e raised to minus 2 kd equal to x, then e raised to minus 4 kd has x square. Okay. So put this here, x square minus uh, 1.5 x plus zero point 0.5 equal to 0. Then find the value of x. What will be the x value? So it is x square. So you'll get the two values x. What are the values you get? Tell me the values of x. What are the values? You can put in the calculator also in the equation degree 2. What are the values you get for x? Anyone got? How do you calculate? Huh, yes, tell me. 1 and 1 and yes, right, 1 and point 0.5. So, seeing this, what value you can take for x? 1 or point 0.5? See, you have 1 is not possible here. You have to take point 0.5. So, here you have to consider this point 0.5. So, x we assumed x is e raised to minus 2 kd equal to what? Point 0.5. Now, what do you do? Take logarithm on both sides. So now it is like point minus 2 kd equal to log point 0.5. So then what is the kd value here? Take what is kd here? Ln point 0.5 divided by minus point 0.2. What is the value? This you can see. Yes. Sorry. Yes, yes. Yes, you will get 0.34. Yeah, I also got 0.34. Yes, this is the answer. Got it. So here, 1 minute. So why we are not taking 1 here? What is the reason why we are not taking 1? Calculate ln 1. What is the value of ln 1? If you take 0, so it becomes 0. See, if you take e raised to minus 2 kd equal to 1, when you take logarithm minus 2 kd, it will become ln 1. And if this value becomes 0, then you will get the rate constant as 0. So now that is not possible. So that's why we are taking zero point 0.5. So if you take zero point 0.5, that means e raised to minus 2 kd equal to zero point 0.5. When we take minus 2 kd equal to ln zero point 0.5. So ln zero point 0.5, I will tell the value. Ln zero point 0.5 is minus, see, ln zero point 0.5 is minus 0.69 divided by kd equal to divided by minus 2. This will get cancelled and divided by 2 will give you 0.34. That is the answer. Got it? Got it now? Understood? Yes. Okay. So this one, the previous one, 3 and 5, that I will recheck and tell you in the next class. This way only this type of questions is solved. Okay. So now it's 8. So we'll continue in the next class. Any doubt in this particular class? Any doubts? Any doubts are there? Experiment this spectrophotometer only told, right? Previous class. Okay, sorry. That I missed. Okay, I will write it down. I thought you told about the spectrophotometer, how it done. That's why I have taken the pictures from my lab also, how it's alkalinity, right? Okay, alkalinity and BOD. Okay, let me type it. Okay, let me write it. What alkalinity? You want experimental procedure of alkalinity. Alkalinity. Uh, okay, then BOD and COD. Okay, okay. These three alkalinity, BOD, and COD. Definitely, class of starting before starting, I will explain with the experimental setup. Okay, alkalinity, BOD, and COD. Okay, I thought it's spectrophotometer. That's why spectrophotometer you guys have done right before in your college. Okay, so okay, this alkalinity, BOD, and COD next class I will write before the starting class. Okay. So, okay, this is clear, right? Anyone has any doubt till this one? Okay, okay, thank you. So, next class I will start with this three parameters, then we go for the other question. So, let me know any other doubt other than this. If you have anything to be more discussed on the next class, I will take. Anyone has anything to say? No. Okay, then let's wind up this class, and I will upload this the slides also with this things which I've solved. Okay, so then you guys can refer. Okay, thank you. Thank you. Okay, thank you.